Hey everyone, welcome back to another video. Today I'm going to take a look at the grade 11 2025 September physical science exam. Let's start with question 1, the multiple choice questions. Question 1.1, a certain chloride is formed when 0.5 moles of element X combines with 1.5 moles of chlorine. Which one of the following is correct, or is the correct empirical formula for this chloride? So question 1.1, I'm going to write element X and element Cl. The ratio, well, they give us is the elements are, the mole ratio is 0.5 to 1.5. Now what you're going to do here is divide by the smallest number. So divide by 0.5, divide by 0.5. And that gives us 1 and 3. So therefore, our empirical formula is going to be XCl3. So the answer is going to be C. Let's take a look at question 1.2. What is the volume occupied by 1 gram of hydrogen gas at STP? So let's calculate number of moles. Number of moles is equal to mass divided by molar mass. The mass of hydrogen is 1. Well, they've given us 1 gram. And the molar mass is 2. Because it's H2. Hydrogen gas is H2. So that's equal to 0.5 moles of H2. So if we want to calculate the volume at STP, we can calculate it by saying V is equal to number of moles times Vm. Number of moles is 0.5. The molar volume at STP is 22.4, and that's going to give us 11.2 dm cubed. So that answer then is A. Let's take a look at question 1.3. Which one of the following reactions below will produce hydrogen gas? Hydrogen gas is produced when an acid reacts with a metal. So the option of acid and metal is A. Question 1.4. Which one of the following pairs represents the conjugate acid and base of HPO4 2-? So if you have HPO4 2-, if you want an acid, you add an H+, and if you want a base, you minus an H+. So if I want to work out the acid, I'm simply going to add an H+, so it's going to become H2PO4, and I'm going to add 1 to the charge, so it's going to be -1. And if I want to work out the base, I'm going to remove 1, so it's going to be PO4, and since I'm removing an H+, I'm going to subtract 1 from the charge, so it's going to become 3-. So the answer here, and I suspect that there was a typo, because it's H2PO4, it should be -1, not 2-. So the answer that we're going to go with here is D. But I suspect that there was an error here. Question 1.5, which one of the following processes is exothermic? Exothermic reactions give off heat, so burning a candle would be the correct answer there. Question 1.6, which one of the following is correct for Boyle's law? So option A says pressure is directly proportional to 1 over V when temperature is constant. And that is true. So the answer there is A. Now, you can use this following equation, the ideal gas equation, to figure it out as well. So PV is equal to nRT. So since N is constant, number of moles, R is constant, and T is constant, then P is going to be directly proportional to 1 over V. Although you can just remember it. Now, question 1.7, which one of the following graphs represents deviation of a real gas behavior, broken line, from an ideal gas behavior, solid line. So we have PV, so we are examining the relationship between pressure and volume. And we know that pressure and volume are inversely proportional. So P versus V should look like this, right? That's an inverse relationship. But we just said that P versus 1 over V, so pressure is directly proportional to 1 over V. So in other words, if you have a pressure and 1 over volume, then it should be a straight line. And you could also switch it. You could also say that V versus 1 over P, that should also give you a straight line. So we want to figure out which one is correct. So A, yes, it does show us an inverse proportionality. However, we need to consider the broken line and the solid line, or the positions. The broken line is going to be a real gas. Now we must remember that a real gas will deviate from an ideal gas. An ideal gas assumes that the molecules themselves occupy no volume, right? So the graph should deviate at low volumes. When the volume is lower, a real gas should deviate this way, because it needs to account for the volume of the molecules themselves. So the graph should not look like this. The graph should look like this instead. So P and V, that should be a solid line. So that's the ideal. And you can see that there's a clear inverse proportionality. But when we are talking about the deviation of a real gas, it should curve upward sooner, because it's going to account, so this right here, this gap, has to account for the volume of the molecules themselves. Now let's take a look at B. So B is showing us V versus 1 over P. And we can see here, and we need to be quite careful, that since the x-axis is 1 over P, if you are going this way, the pressure is decreasing. And if you go this way, the pressure is increasing. So what is this telling us? It's telling us that when the pressure increases, the volume will decrease, which is fine, right? That's what we expect. But as you can see, there is a deviation here. Now we need to figure out, is this deviation correct? So we can see that when the pressure increases substantially, you can see that when it gets close to the y-axis, there is a bend here. And so this here is accounting for the volume of the molecules themselves, right? Because remember, the volume cannot go back to zero. It can't, because the molecules themselves have a volume. They occupy space. And so there has to be that deviation. And so the answer then is going to be B. You can look at D. D is completely wrong, because P and V should not look like that anyway. All right. Now let's move on to question number 2. Methane gas CH4 of mass 34.5 grams is reacted with oxygen in a sealed container. The initial volume of the oxygen was 69.3 dm cubed when measured at STP. So define the term limiting reagent, we'll leave that out. 2.1.2, determine the limiting reagent in this reaction. So let's go ahead first and calculate the information that we can. So CH4, I'm going to calculate number of moles. That's going to be mass divided by molar mass. So the mass that they've given us is going to be 34.5, and the molar mass is 16. And that's going to give us 2.16 moles. Now let's take a look at oxygen, so O2. We can calculate the number of moles. It's V divided by Vm. And the reason why I'm doing that is because they tell me it is a gas and it's at STP. So here I'm going to substitute 69.3 divided by 22.4, and that's equal to 3.09 moles. Now, to figure out which one is limiting, we need to assume that we don't know one value. Okay? Assume that we don't know one value, and then we can do a test. So let's look at the ratio between CH4 and O2. So from the reaction, the ratio is 1 to 2. Now let's assume that I don't know the oxygen, right? So this is going to be 2.16 to X. Now to figure out what X is, you can cross multiply. X is equal to 2 into 2.16, which is equal to 4.32. Now this is the moles that's needed. This is the moles that we have. So we need more than we have. So from this we can conclude that the O2 is limiting. It is going to get finished sooner. Now question 2.1.3, determine the total number of moles of gas in the container after the reaction is completed. So 2.1.3, so because the O2 is limiting, it then means that the CH4 is in excess. Right? So we're talking about the gases. So we're looking at CH4 and we are looking at CO2. So there'll be some CH4 that's left. There'll also be some CO2 that formed. So we can figure out the amount of CH4 that's left over. But before we do that, we need to figure out how much was used. So we're going to use the O2. So the ratio of CH4 to O2 was 2 to 1. Since we know that O2 is limiting, that's 3.09. That's going to be X. We can then do a ratio. So 2X cross multiply is equal to 3.09. X is equal to 1.55. And this is the moles of CH4 that is needed. So the amount that's in excess is going to be the amount that we started with, which is 2.16. So 2.16 minus the amount that is used. So 1.55, and that is equal to 0.61 moles. So this is the amount that's left. Now we need to look at how much of CO2 was formed. So for the CO2, we can do a mole ratio. So we can look at the O2 and the CO2. So O2 to CO2 is a ratio of 2 to 1. If it's 3.09 here, and that's X, we can cross multiply again. 2X is equal to 3.09. X is equal to 1.55 moles of CO2 that forms. So the total number of moles of gas is going to be the excess CH4, which is 0.61, plus the amount of CO2 that forms, which is 1.55, and that's equal to 2.16 moles. Now let's take a look at question 2.1.4. Calculate the percentage yield of CO2 if 58.08 grams of CO2 was formed during the reaction. So let's take a look at the amount of CO2 formed. So the amount of CO2 formed, we just worked it out as 1.55 moles. So for the CO2, this is question 2.1.4. Number of moles is 1.55. We know the molar mass is 44. We can calculate the mass. So number of moles is equal to mass divided by molar mass. 1.55 is equal to mass divided by 44. Now you can cross multiply. And when you cross multiply, you are going to get the mass is equal to 68.2 grams. And then you can calculate the percentage yield. So the percentage yield is going to be how much you actually got. So they actually got 58.08. They were supposed to get 68.2 and times 100. So that's equal to 85.11%. Now let's take a look at question 2.2. The solubility of calcium nitrate is highly endothermic. A 200 cm cubed solution is formed by dissolving 105.6 grams of calcium nitrate in water. Question 2.2.2. Calculate the concentration of the solution. So concentration is equal to mass divided by molar mass times volume. So the mass is 105.6 divided by the molar mass. And we have to calculate the molar mass. So the molar mass is going to be 40 plus, there's going to be 2 nitrogens, so 2 times 14, plus 6 oxygens, so 6 times 16. And that will give you 164. So 164 multiplied by the volume 0.2, and that gives us a concentration of 3.22 moles per dm cubed. Now question 2.2.3, calculate the number of nitrate ions in the solution. So let's take a look at how we can solve this. So CaNO3 will dissolve and will form Ca2 plus and 2 NO3 minus ions. So if we can calculate the number of moles here, which we can, then we can calculate the number of atoms or formula units. So let's calculate the number of moles of calcium nitrate. So number of moles is equal to C times V. So 3.22 multiplied by 0.2, and that gives me what does that give me? Let me double check. So 3.22 times 0.2, that gives me 0.644 moles. Now, since the ratio here is 1 to 2, this is going to be double the 0.644 moles. So that's going to equal a number of moles of 0.644 times 2, which is 1.288 moles. Now, if we know the number of moles, we can calculate the number of ions. So we can use the formula N is equal to number of particles or ions or formula units divided by Na. So 1.288 is equal to N over 6.022 times 10 to the 23. Now you just cross multiply, and that gives you, so times 6.022 times 10 to the 23, and that gives you 76 times 10 to the power 23 ions. Now let's take a look at 2.2.4. How will the temperature of the final solution be affected? And explain. So they tell us that is endothermic. And so that means that the temperature will decrease. Why does it decrease? Because it is endothermic. And endothermic reactions take energy from the surroundings inside. So the overall, the energy of the surroundings will be absorbed. So that's why it is going to decrease. Question 2.3, a 29.05 gram sample of a compound contains 11.62 grams of carbon, 1.94 grams of hydrogen, and 15.49 grams of oxygen. And they want to figure out what is the empirical formula. So simple, we can calculate that. We need to calculate number of moles first. So number of moles for carbon is going to equal 11.62 divided by 12, and that's equal to 0.97. Now the number of moles for hydrogen is going to equal 1.94 divided by 1, which is 1.94. The number of moles of oxygen is going to equal 15.49 divided by 16, and that's going to give you 0.97. Now we can do a mole ratio, carbon to hydrogen to oxygen, 0.97 to 1.94 to 0.97. Now just like in question 1.1, you divide by the smallest number, which in this case is 0.97, to get whole numbers, and that's going to be 1 to 2 to 1. So the empirical formula is CH2O. Question 2.3.2 says, the molecular mass of this compound is 90. Determine the molecular formula. So the molecular mass of the empirical mass rather is going to equal 12 plus 2 plus 16, and that's equal to 30. So the actual molecule has a molar mass of 90. What we have is 30, so that's equal to 3. So the molar mass or the molecular formula is tripled the empirical formula. So we're going to multiply everything by 3. So C becomes C3, H2 becomes H6, and O becomes O3. And so that's our molecular formula. Now let's take a look at question 3. The following reversible reaction takes place in a closed container. The graph below shows the changes in chemical potential energy during the course of the reaction. So question 3.1 says, is the forward reaction endothermic or exothermic? Well, it's going to be exothermic. And that is because the energy of my products is less than the energy of my reactants. Now, question 3.2, calculate the change in enthalpy or delta H for the forward reaction. So delta H is going to equal the energy of the products minus the energy of the reactants. So the products have an energy of 37. The reactants have an energy of 81. And that's equal to negative 44, not forgetting the units, kilojoules per mole. Now, question 3.4. What is the activation energy for the reverse reaction? So reverse reaction means we are starting from here. So activation energy is going to be from here all the way up there. So that value right there. So the activation energy is going to equal 115 minus 37. Now 115 minus 37 is equal to 78 kilojoules per mole. Let's take a look at question 3.5. How does the strength of the bonds within the reactant molecules compare to the strength of the bonds to the products? Well, the products are going to be stronger. And for the simple reason is that they are at a lower energy. So if those molecules are at a low energy, it means that they are more stable and they are going to be stronger. So energy of the products have a lower energy and are more stable. Question 3.6, redraw the graph and show how a catalyst is going to affect it. So a catalyst only speeds up the reaction by reducing the activation energy. So a catalyst, if we are going to use a catalyst is simply going to move. It's going to have a dotted line like that. That's all it does. Now let's take a look at question 4. Question number 4, the balanced equation below represents the ionization of nitric acid in water. Okay, so question 4.1.2 reads, write down the formula or the formulae of the two bases in the equation above. So let's take that out. We can do it here. So this is HNO3, which is nitric acid. So that's definitely going to be an acid. So that means this will be the base. Now, if you look at what happened to the nitric acid, so if that's the acid, NO3 minus will be my conjugate base. And that makes the H3O plus the conjugate acid. So if the question is asking for the two bases, they are basically asking for H2O and NO3 minus. Is nitric acid a strong or weak acid? Give a reason for the answer. So it is a strong acid for the simple reason, and we can see it here, it ionized completely. So HNO3, it gave away the only proton that it had and it became NO3 minus. So because of that, it is a strong acid. So we'll say it ionized completely. And we also need to add the next part, which is to produce a high concentration of H3O plus ions. Okay. Now take a look at question 4.1.5. Write down the formula of an ampholyte. An ampholyte is a substance that can act as both an acid or a base. The ampholyte is water. Water can act as an acid and water can act as a base. It can donate a proton and it can also receive a proton. Question 4.2, a learner performs a titration using a standard potassium hydroxide solution of concentration 0.1 mole per dm cubed and sulfuric acid of unknown concentration. The titration is done 3 times using the same indicator. The volumes of the acid and the base solutions are indicated below. So using the data above, determine the concentration of the H2SO4. Now, this one is quite easy because for a titration, we can use the formula CAVA divided by CBVB is equal to NA over NB, where CA, the subscripts A and B represent acid and base respectively. So we want the concentration of the acid. So CA is the thing we want. VA, the volume of the acid, is given in this column. Now, which value do we take? What we need to do here is we need to take the average. So to get the average, you add all of them and divide by 3. So 21.1 plus 20.9 plus 21.24, and you take the average, that's 21.08. Now, the benefit of using this equation is that we don't even need to convert to dm cubed. So divided by, well, the concentration of the base was 0.1. The volume of the base, you can see here, is 25. And Na over Nb we get from the reaction. We're looking for the coefficients. So in front of the acid, it's 1. In front of the base, it's 2. And now you solve. So Ca is going to equal half times 0.1 times 25 divided by 21.08. And then Ca is then equal to 0.06 moles per dm cubed. Let's just double check. So 0.05 times 25 divided by 21.08. Yep, that is correct. Question 4.2.3. The following is a list of possible indicators. Which indicators should we use? Give a reason. So H2SO4 is a strong acid. And potassium hydroxide is a strong base. Now, a strong acid and a strong base is going to give you a neutral salt. So we want to pick something that is in the pH range of around 7. So that's going to be bromothymol blue. Bromothymol blue. Okay, now let's take a look at question 4.3, which is the 8-mark question here. A solution is formed by adding 30 centimeters cubed of HCl of concentration 0.15 moles per dm cubed to 20 centimeters cubed of calcium hydroxide of concentration 0.1 mole per dm cubed according to the following balanced equation. And the question is asking, determine the pH of the solution. Now, to figure out the pH of the solution, we first need to figure out whether we're going to have acid or base in excess. So we need to go through that whole process of first calculating what is in excess and then calculating the number of moles that's in excess. So we'll start with the calcium hydroxide. For the calcium hydroxide, we know the concentration, 0.1. We know the volume, which is 0.02. We can then calculate the number of moles. So number of moles is equal to C times V. 0.1 times 0.02, which is equal to 2 times 10 to the minus 3 moles. Now for HCl, we know the concentration 0.15 and we know the volume 0.03. We can calculate the moles again. So 0.15 times 0.03, which is equal to 4.5 times 10 to the negative 3 moles. Now to figure out what's in excess, we need to do a ratio. So we'll do a ratio of calcium hydroxide to HCl. Now imagine we don't know one of them. So 2 times, well, it's 1 to 2. So then 2 times 10 to the minus 3, and let's call that x. So if I want to calculate x is going to equal 2 times 10 to the minus 3, which is equal to 4 times 10 to the minus 3 moles of HCl that is needed. Now we have, if you look at this, 4.5 times 10 to the minus 3 is greater than 4 times 10 to the minus 3. So we have more than we need. So that means that HCl is in excess. So because the HCl is in excess, we can then conclude that since it's an acid, the pH at the end is going to be less than 7. Now let's go ahead and calculate it. So what we need to do now is work out how much is in excess. So we can say the HCl that's in excess is going to equal how much that we have. We have 4.5 times 10 to the minus 3, and we needed 4 times 10 to the minus 3. So we have an excess of 0.5 times 10 to the minus 3. Now this HCl is now sitting in a container that had 30 cm cubed and then was added to 20 cm cubed. And so the total volume that the HCl is now sitting in is 50. So we can calculate the concentration of the HCl. It's going to be 0.5 times 10 to the minus 3 divided by 50 cm cubed over 1,000. So we convert that. And that's going to give us a concentration of 0.01 moles per dm cubed. Now remember, to calculate pH is equal to minus log of the concentration of H3O plus or H plus, whichever one you want to use. Now we don't know the concentration of the H3O plus. We know the concentration of the HCl. However, we also know that HCl is a strong acid, and so it will ionize completely. So it's going to give H plus and Cl minus. Now, because it's all in the same container, the number of moles of this is going to equal to the number of moles of that, which is equal to the number of moles of that. The ratio is all 1 to 1 to 1. And because it's in the same container, the concentration of this is going to be the concentration of that, which is going to be the concentration of that. So if we want the concentration of the H3O plus, it's going to be the same as that. So that's going to be 0.01. So pH is going to equal minus log of 0.01, and that's going to equal 2. And that's what we expected. We expected a pH that is less than 7. Now let's take a look at question 5.1, which is question 5, the last question in the paper. A gas is contained in chamber A, which has a volume of 5.3 dm cubed, and is sealed off from container B, which has a volume of 3.2. Initially, only chamber A contains gas, while chamber B is a vacuum. The chambers are then connected by opening a valve between them, and the gas is allowed to expand freely. The temperature remains constant and no gas escapes. So question 5.1.2, explain in terms of Boyle's law what happens to the pressure of the gas after the valve is opened. So when you open the valve, the volume that the gas can occupy increases, right? And we know that according to Boyle's law, pressure and volume are inversely proportional. So if the volume increased, the pressure will decrease. Question 5.1.3. Calculate the final pressure of the gas after the valve is opened. So P1 V1 is equal to P2 V2. The pressure at the beginning is 135.2. The volume at the beginning is 5.3. That's equal to P2. And the volume that the gas can occupy once the valve is opened is going to be 5.3 plus the 3.2. So we can then solve. So P2 is going to equal 135.2 multiplied by 5.3 divided by, and that's going to be 8.5. And then P2 is then equal to 84.30 kPa. Question 5.2, sketch a graph that shows the relationship between pressure and volume. Okay, so pressure and volume, inverse proportionality. Okay, question 5.3, state the conditions of temperature and pressure under which a real gas behaves as an ideal gas. So a real gas will behave as an ideal gas at a low pressure and at a high temperature. And lastly, question 5.4, which real gas behaves the closest to an ideal gas? So one of the properties of an ideal gas is that an ideal gas is assumed not to have any interaction with other molecules. There's no intermolecular forces. So what we need to be looking for are noble gases. And we need to look for a noble gas that has the smallest size. So if you go to our periodic table, we can see here that these are all my noble gases. And the smallest noble gas is going to be helium. So the answer to this question is going to be helium. Okay, helium, and the reason is because helium is unreactive, right? There's going to be little to no forces of attraction, or you could say intermolecular forces if you want, and you could say it's also quite small. It is the smallest of the noble gases, and so its volume is not going to play a significant role. And that's the answer. Again, everyone, thanks so much for watching. If you stuck around, don't forget to leave a like, share, and subscribe. And I'll see you in the next video. Bye-bye.